Thank you for your interest in our paper. I am Yi-Chun Lee, and will introduce to you learning 3D part assembly from a single image. In this paper, we aim to solve an IKEA furniture assembly-like problem. We define the problem of part assembly specifically in a single image setting, as given an image and a set of post-canonicalized input parts, where the center and rotation of all parts are PCA aligned, and the scale of each part is normalized in such a way that the largest part in the shape has diagonal of its axis-aligned bounding box resized to 1, and the rest of the parts are scaled accordingly to preserve the shape structure. The goal is to find the rigid body pose for each part in the camera space such that the final shape resembles to the shape depicted in the image. In the assembly setting, the given set of parts is exactly the number of parts needed to achieve the target assembly. We propose a two-module network that first conducts a conditional segmentation to extract a mask from the image for each of the corresponding part to build a 2D to 3D grounding shown in the top section of the pipeline figure. With the geometry to image grounding, we then embed all available image and geometry level part features to a part graph, and conduct a two-stage of graph convolutions composed of a post-proposal graph conv and a post-refinement graph conv, and we'll go through these modules in detail. The first module is the instance segmentation module, where we use the conditional UNet to extract a mask from the image for each of the corresponding parts. Specifically, we use pointnet to extract a 3D feature and add an instance one-hot label to differentiate between the geometrically equivalent parts, such as the back bars of a chair or the legs of a table. Then we maxpol to get a global feature so that when extracting the current mask, the network is aware of its context, which is the existence of other parts. Finally, we stack together all mask proposals through a softmax operation to make sure that each pixel only belongs to one part. With the 2D segmentation, we can infer part poses using a two-stage of graph convolution. We build a part graph by embedding each part as a node in the graph. We then connect parts by defining different part relationship edges. We combine a set of part-specific feature and contextual features to construct nodes for each part. Specifically, the part-specific features include the 3D feature extracted using pointnets, as well as the instance one-hot vector used in the segmentation prediction stage. Additionally, a part-specific 2D feature is added by extracting one-channel ResNet feature from the predicted masks. We also add a set of contextual features, such as the 3D global feature used in the segmentation stage and the image ResNet feature to offer a global perspective for each part node. For the two sets of edges, we first connect the geometrically equivalent parts. For example, the legs of a chair are geometrically similar and are most likely to be in parallel or symmetric relationship with one another. So we want to use this geometry property to propagate post information from visible parts to invisible parts with the same geometry, so to help post hallucination for parts occluded in the image. The message passing mechanism helps parts to balance with one another when they fight for the same location. With two iterations of graph convolution, we aggregate all edge features to regress the first stage of part pose. We work the predicted poses onto each point cloud and to construct a preliminary shape to be used for the second stage of graph convolution. Because parts need to be in contact with one another, parts floating in midair disobey physics laws in the furniture assembly setting. So we want to use the intuition that local parts relationship might propagate to other parts. We then use a set of nearest neighbor edges to implicitly enforce these constraints. Then conduct the second stage of graph convolution, aggregating all edge features to find the final post prediction, namely the translation and rotation for each part. We treat the segmentation module and post prediction module separately. We supervise the instance condition mask prediction using the soft IOE loss between the ground truth image segmentation and the predicted mask. We can supervise the post prediction module using translation L2, rotation L2, rotation transfer distance, as well as the final example shape transfer distance loss. Specifically, translation L2 means L2 distance between the translation prediction and the ground truth translation in Euclidean space. Applying the predicted quaternion and the ground truth quaternion onto the part point clouds forms a rotated part geometry in the part-centric coordinate space. Additionally, as the experiment shows, the chamfer distance has local minima in cases where there exist delicate geometric details in the part geometry, such as the chair legs shown in the image. Chamfer distance is not sensitive to such part geometries, where an upside-down prediction will also evaluate to low loss values and resulted in reduced prediction accuracy. Thus, we add a L2 rotation loss, which is the L2 distance between the predicted rotated parts and the ground truth rotated part to facilitate the rotation prediction in these scenarios. For the part accuracy, we select the threshold of 0.1 and calculate a two-way chamfer distance between the predicted part pose and the ground truth part pose, which then gives us an accuracy score. For the shape chamfer distance, we calculate the two-way chamfer distance between the predicted and the ground truth assembly. We compare with three baseline methods, using different mechanisms to deal with geometrically equivalent parts to propose different poses for the same point cloud geometry. The first one is GRU-based method. For each part geometry, this method sequentially predicts K poses, and we take the first N proposals and conduct Hungarian matching to match with the N ground truths when evaluating the method. The second method is instance one hot, which directly use MLP to infer poses from the geometry and the image. The instance one hot label is used to differentiate between the equivalent point clouds, and we conduct Hungarian matching to match the ground truth poses regardless of the one hot encoding. The third baseline improves upon the second baseline by adding our context-aware 3D global feature. Each pose projection not only considers the part-specific 3D feature and image feature, but also the 3D global feature to offer more context. We conduct experiments on the three largest furniture categories of chairs, tables, and cabinets. And we also have two different modalities for each category, because we cannot assume that the real-world chairs and tables follows the same partnet level 3 granularity. To be able to handle any set of geometry for a given shape instance, we add a mixed modality of parts, which consists of shapes of parts that randomly stop in different levels of the partnet semantic tree. The quantitative results under the metrics of part accuracy and shape chamfer distance demonstrate that we outperform the baselines. Additionally, we also compute the accuracies for visible and invisible parts separately, because one of the key challenges of the part assembly problem lies in post-hallucination for occluded parts. We demonstrate that we outperform the baselines for occluded parts as well. Qualitative results also demonstrate that we outperform the baseline methods. Our prediction results are more structurally sound and leverages more post-information revealed by the image.
Thank you for listening.